Assalamualaikum and greetings. This presentation is for the UCS551 group project on concrete compressive strength. The aim is to classify concrete samples into two strength ranges based on mixed ingredients and curing age using supervised learning. This project is presented by Group 1. The members are Siti binti Sulaiman, Sharifah Jazmine Khadijah binti Syed Abdul Rajak, and Aloysius Ulin, anak Sandah. Each member contributes to different parts of the workflow and reporting to ensure complete coverage.
Next, we're moving to project background. Concrete is one of the most widely used material in constructions, especially in buildings, bridges, and roads. An important property of concrete is its compressive strength, which measures how much load it can carry before failure. This is critical because the strength of concrete is directly affect the safety and durability of the structure. The strength also depends on its mixed materials and curing edge. Here, we apply supervised learning using a classification approach to predict compressive strength. The model learns the relationships between the ingredients and its resulting strength. This approach helps engineers design better concrete mixes, reduce laboratory testing, save time and cost, and ensure that required strength standards are achieved, supporting safer construction practices. Next, about the project objective. In this project, we use supervised learning to predict the compressive strength of concrete using a reliable dataset with a clear target variable. We first analyze the dataset, checking attribute types, patterns, and missing value to ensure it was ready for modeling. Next, we clean and pre-process the data in Altair RapidMiner. This included defining the target variable, normalizing the input, and preparing the dataset for training. We then trained 3 supervised learning models and evaluated them using data splits and cross-validations. By comparing their performance, we selected the best model for predictions.
Now, I will explain about data understanding. The dataset used in the concrete compressive strength is obtained from Kaggle. It contains 1,030 records and 9 attributes. 8 numerical attributes are used as predictors, representing mixed ingredient quantities in kilogram per cubic meter and curing edge in days. The target attribute is compressive strength in megapascal and is standardized as strength in RapidMiner to maintain consistent attribute, naming throughout the pre-processing and modeling. Data quality checks show no missing values, indicating that imputation is unnecessary. Duplicate rows are present and can bias training and evaluation by over-representing certain mix design. Therefore, duplicate removal is included in pre-processing. Several ingredient columns contain many zero values, which represent valid mixes where a component is not added rather than missing data. In addition, curing edge values are concentrated at standard testing duration, such as 28 days, which suggests uneven representation across edge categories. Initial checks show that compressive strength usually increases when cement content is higher and when curing edge is longer, while high water content is usually linked to lower strength. The predictors also do not appear to be strongly dependent on each other during initial inspection, so this is not expected to heavily affect the model. This finding guide the RapidMiner process design. The target attribute is renamed for consistency, duplicate rows are removed to reduce bias, strength is discretized into 2 classes for classification evaluation, and only 1 target label is assigned using set role. Attribute selection is used to prevent leakage, and normalization standardized predictor scales to support stable learning, especially for neural network.
This section explains how the raw data set is prepared in AI Studio RapidMiner before modeling begins. The goal is to produce a clean dataset with a valid label and standardized predictors for fair comparison across models. First, a project repository is created to keep all processes and datasets in one organized workspace. Next, folders are prepared to separate raw data, clean data, and process files, improving file management and reducing confusion during modeling. The dataset is imported into the repository to ensure a consistent source is used. After that, the dataset is retrieved into the pre-processing canvas, so operator-based cleaning and transformation can be applied systematically. The target attribute is renamed to strength to standardize naming in modeling outputs and result tables. Then, remove duplicates is applied so repeated rows do not inflate training patterns or bias evaluation. Strength is discretized into 2 bins, producing range 1 and range 2. which converts the task into classifications. Next, set role is used so strength becomes the only label, ensuring the workflow follows the requirement of one target attribute. Select attributes is applied to confirm that only relevant predictors are used and the label remains correctly assigned. Normalise is then applied because the predictors have different measurement scales, and standardization supports stable learning, especially for neural network. The clean dataset is stored in the repository, so the same prepared dataset is reused in all modeling experiments. This prevents inconsistency caused by repeating pre-processing separately for each model and supports fair model comparison. This section starts the modeling phase using split data evaluation using Naïve bias, and accuracy is recorded to compare the three classifiers that are tested on the two strength ranges. The clean dataset is retrieved from the repository to ensure modeling uses the prepared version only. Then, split data divides the dataset into training and testing partitions so the modeling is evaluated on unseen data. Naïve bias is trained using the training partition to learn the relationship between predictors and the strength class. The trained model is then applied to the test partition using apply model to generate predicted classes. Performance operator calculates evaluation metrics, with accuracy used as the key comparison measure. The accuracy result is recorded as the baseline performance for Naïve bias under the selected split ratio. The split data ratio is adjusted to observe how training size affects performance. Accuracy values across split ratios are compared to check whether the model is stable or sensitive to partitioning. This slide introduces decision tree under the same split data evaluation approach. Decision tree is suitable because it can form rule-based boundaries that capture interactions among concrete mixed variables. The Naïve bias workflow is duplicated to keep evaluation setting consistent. The learner is replaced with decision tree, while apply model and performance remain unchanged to ensure a fair comparison. The process is executed and the decision tree accuracy is recorded for each split ratio. The model output is also reviewed to confirm that the decision structure is produced correctly and corresponds to the strength classes. This slide introduces artificial neural network under split data evaluation. Neural network is included because it can model complex and nonlinear boundaries that may exist between range 1 and range 2. A conversion step, such as nominal to numerical, is included where needed to ensure the learner receives compatible input format. Then, neural net is trained using the training partition to learn patterns from the standardized predictors. The trained neural net model is applied to the test partition using apply model to generate predictions. Performance then reports accuracy so neural net results can be compared directly with Naïve bias and decision tree. Cross-validation is used to produce a more reliable estimate of model performance compared to a single trained test split. Naïve bias is evaluated as a baseline under K-fold testing. The clean dataset is retrieved from the repository as the modeling input. Cross-validation is added to the process to replace split data. This ensures evaluation uses repeated fold-based testing. Inside cross-validation, Naïve bias is placed in the training subprocess, and apply model and performance are placed in the testing subprocess. The number of folds is set to 5, then the process is executed to obtain average accuracy. The number of folds is changed from 5 to 10 to test whether accuracy remains stable with more partitions. Similar accuracy across folds indicates the model performance is consistent rather than dependent on one specific split. Decision tree is then evaluated using cross-validation to compare performance under a more robust validation method. This reduces the risk of overestimating accuracy due to a favorable split. The clean dataset is retrieved again to ensure consistent input. Cross-validation is used with decision tree placed in the training subprocess. This maintains the same evaluation structure as the Naïve bias cross-validation test. The cross-validation subprocess is completed using apply model and performance in testing. The number of folds is set to 5 and the process is executed. Accuracy is observed and recorded for comparison. The number of folds is increased to 10 to confirm reliability. Decision tree accuracy remains high across fold settings, supporting that it generalizes well on the clean dataset. Artificial neural network is then tested using cross-validation. Because the label is nominal, a conversion step is included so the neural network can operate correctly. The clean dataset is retrieved as input. Nominal to numerical is added to convert nominal predictors into numeric format if needed, ensuring compatibility with the neural network learner. Cross-validation is added after the conversion step to evaluate performance reliably. The cross-validation operator is opened and neural net is placed in the training subprocess. Applied model and performance are placed in the testing subprocess. Accuracy is recorded for K5 to establish baseline cross-validation performance. Then, the fault setting is changed to K10, then rerun to compare stability and final accuracy. This section summarizes the outputs from pre-processing. The focus is on measurable changes in the dataset after cleaning. The raw dataset is compared with the clean dataset to show the impact of cleaning, including row reduction after duplicate removal while maintaining the same set of attributes. Strength is confirmed as a nominal level with two classes supporting classification evaluation. The class distribution chart shows how records are divided between range 1 and range 2, which is important because imbalance can affect accuracy interpretation. The normalized plot for age, cement, and water shows overlapping patterns between classes, suggesting that models capturing complex boundaries are beneficial. Then, the section summarizes the outputs from modeling. The focus is on the accuracy comparison across classifiers. The accuracy table and graph compares naive bias, decision tree, and neural network under split data and cross-validation settings. Decision tree and neural network show stronger accuracy than naive bias, and cross-validation results support the final model choice based on both high performance and stability.
Next is for discussion part. Impact of pre-processing. Pre-processing improve modeling readiness and evaluation fairness. Duplicate removal reduce repeated records that can bias performance. Strength was converted into two classes, so classification accuracy could be measured. Only one attribute was assigned as the label to ensure a consistent target definition. Predictor normalization, standardized skills, and supported stable learning, especially for neural net. All models were trained and tested using the same clean data set for fair comparison. Model performance comparison. Model results show clear performance differences. Naive bias achieve moderate accuracy, which is expected because it performs best when predictors behave independently. Decision tree produced the highest and most consistent accuracy, indicating that rule-based splits effectively separate the strength classes. Neural net also achieve high accuracy, supporting that the dataset contains complex patterns that benefit from nonlinear learning. Overall, decision tree provides the strongest performance for this classification task. Next is validation reliability and limitation. Split data result may change depending on the chosen ratio, and a very small test sets can produce optimistic accuracy values. Cross-validation provides a more reliable estimate because results are averaged across multiple faults, improving stability and confidence in model ranking. A key limitation is that discretizing strength into two classes simplifies the original megapascal values, so detailed strength prediction is not provided. To strengthen evaluation, confusion metrics and additional metrics such as precision and recall should be reported alongside accuracy.
We're moving to the conclusions. Overall, the decision tree model was the best performing among the three models we tested. It achieved the highest accuracy of 90.73% using a 70-30 data split ratio, making it the most reliable for predicting concrete compressive strength. There are still opportunities to improve the model's performance. One key approach is features engineering. By creating new variables such as water to cement ratio or aggregate ratio, we may capture additional patterns in the data that current features do not fully represent. Another improvement is to enhance data sampling and augmentation technique. Better sampling strategies can address any imbalance in dataset and make the model more robust across different mixed design and current edge. Overall, while the decision tree provides strong predictions, applying features engineering and improved data handling could make our predictive systems even more accurate and useful for civil engineering applications.
Thank you for listening to the presentation. Appreciation is extended to the lecturer for the time and attention.